What is the largest number dividing both 12 and 30? One way is to list the common divisors of both numbers. The greatest of them is 6, so the greatest common divisor of 12 and 30 is 6. But there's a better way to do this, which is more than 2,000 years old. Here's the whole trick. Divide a by b with quotient q and remainder r. Then the greatest common divisor of a and b equals the greatest common divisor of b and r. Why? We can prove that anything dividing a and b also divides r, and anything dividing b and r also divides a, so their set of common divisors is the same. Hence, their greatest common divisor is also the same. Check it on 25 and 15. The remainder is 10, and both pairs have a greatest common divisor of 5. Now, we repeat until we get a remainder of 0. Take 490 and 110. The first time we divide, we get a remainder 50, then 10, and then once more a remainder of 0. When the remainder hits 0, the last non-zero remainder is the greatest common divisor, in this case, 10. That is the Euclidean algorithm. Try a larger one from the Mandelbrot competition, 25,001 against 2001. 3 divisions give us a remainder of 989, then 23, then 0. The greatest common divisor is 23. Now, a competition classic from the AIME exam. The sequence an equals n squared plus 100. For each n, let dn be the greatest common divisor of consecutive terms. How large can dn get? Euclid says subtract. Consecutive terms differ by 2n plus 1, so dn is the greatest common divisor of n squared plus 100 and 2n plus 1. One clever combination helps us out. 4 times the quadratic minus 2n plus 1 times 2n minus 1 gives us exactly 401. So dn always divides 401 no matter what n is. At n equals 200, both terms are multiples of 401. The answer is 401 for the greatest common divisor. The core idea here is to always trade a pair of numbers that you want to compute the GCD of, and then replace it with a smaller pair. That is the entire algorithm. And the same move goes much further. It collapses towers of exponents, and it runs secretly inside the Fibonacci numbers. We'll take a look at that next time.